Interchapter C is now going to address how to identify the configurations about a stereocenter. And we already know that the configurations are R and S. But now we're going to learn the tricks and the skill sets on how to actually assign those configurations. And then we are going to learn about how to assign Z and E configurations to a double bond. So the IUPAC rules for assigning configurations, they have some 3 simple steps that we need to take in order to do this. And in order to, there's a name right here. That's not the button. So the rules to figure out the configuration is however you pronounce that. Okay? That's the special name. You don't need to remember that name. Okay? But you do need to understand these 3 rules or steps to assigning the R and S. These are the basic steps. So there's going to be additional steps as we progress through the lecture. But these are the 3 basics to get us started. So what it is telling us to do is if we have a molecule with a stereocenter. So one that looks like this. Let's see, a carbon with a chlorine with a nitrogen Okay, so if we have a stereocenter like this, and we know it's a stereocenter because there's 4 different groups. Step 1 says that we need to prioritize the 4 groups about that stereocenter in a priority of 1 through 4, 4 being the lowest and 1 being the number 1 priority, or the top priority. And the way you prioritize these 4 groups, the chlorine, nitrogen, oxygen, and hydrogen, is looking at the periodic table and looking at the atomic mass. So if we look at chlorine, we see we have an atomic mass of 35.45. And if we look at nitrogen, it's 14. If we look at oxygen, it's 16, and hydrogen is 1. So you just rank the groups based off of their weight. Now, I'm not looking at the weight of the OH or the NH2. I'm just looking at the weight of the atom that is directly attached to the stereocenter. So the chlorine would get priority 1. Let's see what's bigger between oxygen and nitrogen. Oxygen is larger, so that gets priority 2. Nitrogen gets priority 3, and then hydrogen gets the lowest priority with a 4. Okay. Now, this is step 2 is critical for your success in being able to identify the configurations, is that the lowest priority, right here, the lowest priority may not be a hydrogen. It may be a different group. The lowest priority group has to be pointing away from you, which simply is saying it needs to be the dash. Lowest priority groups need to point away from us in the dash. And then you take your pencil or pen and trace through numbers 1, 2, and 3. You don't worry about number 4. So if I trace 1, let's make sure this, let's clear that up. If we go from 1 to 2 to 3, what direction is that arrow going in? We see that it is going counterclockwise. And when it goes through numbers 1, 2, and 3 in the counterclockwise direction, that is going to be a S configuration. Okay. Now let's do another problem here. What if we have this? Good. Remember the steps. It says prioritize things. 1, 2, 3, 4. Step 2, we make sure the lowest priority is a dash, which it is. And then we just trace through 1, 2, and 3. 1, 2, 3. We can see that that is going in the clockwise direction. So that makes this stereo center a R. So those are the simple, or not simple, the basic steps for assigning R and S. Now you can see where the mistakes can possibly come in. So this is an R. No doubt it's an R. But what if you made a mistake and assigned nitrogen as priority 2 and oxygen as priority 3? You would be like, okay, well, 1, 2, 3, counterclockwise, so that's an S. And that's 100% wrong, and you won't get any credit for it. Because obviously, I know you guys have the skill of tracing an arrow through 1, 2, 3. That's easy, right? That's not, and it's easy to know that and to memorize that counterclockwise is S. That's not hard. Okay? But what gets tricky is the prioritizing. That has to be done correctly. Okay? So that makes it R. The other thing that gets students all the time is, let's say, the hydrogen or the lowest priority is not a dash. Let's change it up to this. What if we had this? So we go through steps 1, which simply states we need to prioritize things. So that's 1, 2, 3, and 4. Okay? And then if you forget and skip step 2, you'll go right to step 3 and go like this and say, hey, that's going in the clockwise direction, so that's an R. But you skip step 2. You have to get the lowest priority group pointed away from you. Okay? So let's go back to the slide before we go further into that so you can see what's going on. So if we have, okay, let's get to a slide that we want to talk about. Let's see here. Okay. Let's talk about this molecule here. So step 1, we have to prioritize all the groups. And we see that we have prioritized things correctly. Bromine is the largest, chlorine's the next, the carbon is third, and hydrogen's the fourth. Step 2 states that we need to get the lowest priority group into the back, or the dash. So you can do that by rotating. about the bond. So let's say here, let's draw this molecule. So what do we have? We had carbon. Let's do a different color. So we have carbon, bromine, methyl group, hydrogen, and then our chlorine. Okay. So if this technique works for you, this is great. What you're going to do is grab the bromine with your hand, and you're just going to spin the whole molecule by grabbing onto the bromine. So look at the bromine as like a handle or a knob. You're grabbing it and you're spinning the whole molecule. And you're going to spin it in such a way that you're going to get the hydrogen to become a dash. So you rotate it and you get the hydrogen as the dash. But then the tricky part, if you can't see it, you need to make a model. Where is the chlorine going to be and where's the methyl group going to be? Well, if you spin it to get the hydrogen into a dash, you're going to have the chlorine in the plane and you're going to have the methyl group coming out at you. Okay. And now so that's like step. So step 1 was to prioritize everything. Step 2, make sure the hydrogen's a dash, or the lowest priority is a dash. So this was our original problem. So step 2 would tell us, hey, we need to spin the molecule and orient it in which to get that lowest priority into the dash. And then we do what we are good at, tracing the numbers 1 through 3. 1, 2, 3. We are going in the clockwise direction, so that would make this, both of those, R's. Okay? But not everyone is good at taking molecules and spinning them and rotating them in three-dimensional space. So there's some tricks for those people who have a hard time seeing things in their head. Okay, here's the first trick that you can do. So when the first step is to prioritize things, which the slide has done for us very nicely. Step 2 says, hey, the lowest priority isn't a dash. But I don't like rotating molecules because I get confused. So what you can do is just leave it alone. Don't do anything. And proceed to step 3. And you trace it like you normally would. And you can see going from priority 1, 2, and 3, we get the S. We're going counterclockwise, which is an S. But then you just simply take the opposite of what you just calculated. So we know that this is a R. That has an R configuration. Yes, the way I'm tracing it through the priorities 1 through 3, that's going counterclockwise, and that is an S, that is true, but because we're violating step 2, we just take the opposite of what we just calculated. So that has a R. Okay, do you see how when I go here, that's the exact same molecule. That molecule on the slide is this molecule here. I just rotated it. Exact same molecule, and it has an R. So by golly, this one has to be R, right? Because they're the same molecule. But this is just another way to find the configuration. Just leave it alone. But here's the cautionary tale. This trick only works, only works if the hydrogen or the lowest priority is a wedge. Okay? You can only do this opposite trick when the lowest priority is a wedge. If the hydrogen or the lowest priority is in the plane. Okay? If the lowest priority right here, we can rank them 1, 2, 3. If it's the lowest priority is in this plane, and you know it's in the plane by looking at this bond, it's not a wedge or a dash. If it's in the plane, that trick, the opposite trick that I just showed you, does not work. You have to take this molecule that I just drawn and you have to rotate it. Okay? You have to. Or there's another trick. So let's say we have, let's look at this molecule here. So I'm going to rotate it. Let's get that hydrogen into the plane. Okay, so we need to make sure we're doing this right. So that means the chlorine would now become the wedge and the methyl group is on the dash. Okay? So remember, or just notice that this molecule in blue right here, this guy right here is the exact same molecule over here. So we have to get the same configuration. It has to be an R. But what if this was what was given to you on the exam? If that was given to you on the exam, you had no idea about this guy to my left. So what you have to do now, step 1 says we prioritize. 1, 2, 3, 4. Step 2, we clearly see that the lowest priority is not a dash. So that's a problem. We can't do the opposite trick because the lowest priority is not a wedge. So what can you do? You can do a switcheroo trick. Okay. What you can do is you identify this molecule as the original, and then you redraw the molecule, but you do a switch. And what you're going to switch is you're going to take the lowest priority and switch it with the dash group. So we can see now the hydrogen is there and the methyl group is here. And the chlorine just didn't move, it just stayed. Now, this molecule that I just drew is not the same thing as the original. And the reason is because I took those two bonds, broke them off, and switched them. When you break two bonds and switch them, you're going to change the stereo. You're going to change the configuration. So this one right here is our trick molecule. This is to help us. Okay? So now with the trick molecule, go through steps 1 through 3. Step 1, prioritize. Step 2, is the lowest priority group a dash? Yes, it is. Now we just do our, go through the number, go 1 through 2. 1, 2, 3. And what direction are we going in? Counterclockwise. And that makes us have an S configuration. So the trick molecule has an S configuration. But we are interested in what is the configuration of the original molecule. And the way you figure out the original is you just take the opposite configuration of the trick molecule. So that makes this guy an R. Alright? So you see how this molecule circled in red has an R configuration and is exactly the same configuration as this one? And it has to be, right? Because molecule A is the same thing as molecule B. They're the same molecule. They're identical. Okay? We're just looking at the same molecule in different orientations. This one we have the methyl or the hydrogen as the dash, and here it's in the plane. Okay? So this is the third way of figuring out configurations, is the switcheroo trick. But this can get confusing sometimes, that students will look at the trick molecule and do it correctly and they're full of confidence and they put the S down as the answer. They fail to realize that this trick is used, the trick molecule is used so you can find the opposite of it for the original. So watch yourselves if you choose to do that trick. Now, there's 3 ways of doing this. Some people like to just stick with the first way, which is rotate the molecule. Some people like to, if the lowest priorities is a wedge, they like to do the opposite trick. Or you can do the switcheroo trick. Okay? You find what works best for you. Now, when you name a molecule and you know that you have a stereocenter, you need to identify in the name if it's an R or an S. So if we see this molecule here, we see that there's one stereocenter, and we know that the stereocenter is a R. And so you just stick the R at the beginning of the name. So R1 bromo 1 chloroethane. Really, really straightforward. Okay. Now, what if you have a molecule with 2 stereocenters? How do you name that? Okay, so I'm going to skip ahead here. So we have this molecule shown, and we see that there's 2 stereocenters. Okay, so this is how you would name it with the skill set that you already have up to this point. But now that there's 2 stereocenters, we need to designate if they're R or S in the name. So what we do is we assign what's R and what's S, okay? So we will figure out how to assign the R and S in a minute. I'm just focusing my attention on the name, how to name it, okay? So this stereocenter right here at carbon 1 is a R, and the stereocenter at carbon 4 is an S, okay? So just bear with me here. So there's 2 ways you can name this molecule. You can see going back, there's the original name. So how can you incorporate the R and S into this name? Well, there's 2 ways. The top one is where you put the configuration next to the substituents. So you can see that the 1 bromo, 1 chloro is referring to these groups right here, which are attached to carbon 1. So you just stick the R right next to those substituents. And you can see the fluoro and the nitro group are right here, and that is on carbon 4, and that has a S configuration. So it could be written that way. I prefer the bottom way. That way I just keep the name the same as here. So you just keep the name the same. And then to the left, you just specify what carbon is the stereocenter at. Well, carbon 1 has a stereocenter, and at carbon 1, the configuration is R. Carbon 4 is a stereocenter, and its configuration is an S, and you put those into parentheses. I like the bottom way better. That's just a personal preference. If you did this one right here as an answer choice, you would get 100% of the points. Okay, so it doesn't matter to me. You pick what works best for you when you name molecules. Okay, now I've been showing you how to find or designate the configuration of the stereocenters when there's only one. But organic chemistry is more complex than that, and you're going to have multiple stereocenters in a molecule. So the trick is you just look at each stereocenter one at a time. Treat the entire molecule as if there's only one stereocenter. Okay, and you just follow what you've learned. So step 1. So let's look at the stereocenter at carbon 1 and figure out what it is. What is the first step? Prioritize. So we can see we're looking at this carbon. What are the 4 groups that are directly attached to it? Well, we have a hydrogen, a chlorine, a bromine, and then this carbon right here. Okay? Now we prioritize the groups. Bromine would be 1, chlorine 2, carbon would be 3, and hydrogen 4. And in this particular example, lucky for us, the lowest priority, step 2, says the lowest priority needs to be a dash, and it is. So lucky for us. Step 3, just trace through the priorities. 1, 2, 3, we see we're going in a clockwise direction. Gives us an R. And then you do the exact same process for the second stereocenter. Follow all the same steps. And we can see that the lowest priority is once again a dash, so we've lucked out. It's pretty nice. Okay? So you just treat each stereocenter as if it's the only one. Okay, and you just follow the same steps that we've been doing. Now in this example, we find the stereocenter. Where is the stereocenter? It's right here. That's our stereocenter because we have 1 group, 2 group, 3 group, 4 group. There's 4 different groups. So that's our stereocenter. So we've identified that. That's great. Now we go to step 1, which says to prioritize. We see we have a chlorine. That's really large. And we see a hydrogen, and that's the smallest. So we have assigned priorities 1 and 4. But looking here, we have a carbon and a carbon. So there's a tie. Which one takes priority over the other? They're both carbons. So we have another trick to help us break ties. There's going to be a tiebreaker. And here's the rules. It's just easier and better, I feel, just to show you how to do it. Okay? So here's the molecule again. So we've already assigned the highest and the lowest priority. So what you do is you can see that this carbon, well, right here's a carbon and right there's a carbon. It's the same priority. So what you have to do is you have to expand. You have to then look and see what is directly attached to this carbon. Okay? And we can see those atoms in red. It's the hydrogens, the 2 hydrogens, and this carbon. Now, we don't count the carbon that's attached to the stereocenter, okay? Because all we care about is what is directly attached to this carbon except what's before it. So at this carbon, we see that we have a carbon, hydrogen, hydrogen. And you write those down, okay? So you can write them down. Let's just say we have a hydrogen, carbon, hydrogen. Let's say I wrote it in that order. Okay? That is a mistake. once you find all the atoms that are directly attached to this carbon here, which are shown in red, you then take that list that you made and you prioritize them by size. And so you can see how we've actually wrote it like that. CHH. Okay? So after you've identified the atoms that are attached, prioritize them by order of size. Okay? And we do the exact same thing for this carbon right here. What's directly attached to it? We see 3 hydrogens. And so that's an HHHH. Okay? Then once you have that data, you are looking for the first point of difference among that set. So we have this set and that set. And we just go from left to right. I see a carbon and a hydrogen. There's my first point of difference. At that point of difference, which one has the largest atom? A hydrogen or a carbon? Clearly, carbon is larger than the hydrogen, so that breaks the tie. And this carbon right here, because that breaks the tie, is going to get the second priority. And that's how you break tiebreakers. You see what's attached to it. Okay? Sometimes you don't break the tie on the first try. Okay? So if we have a molecule that looks like this, and here's our stereocenter right there. We can clearly see we have a chlorine, a hydrogen, carbon, and a carbon. These carbon groups clearly are different groups because look at it. There's this thing and that group. They're completely different. So we know it's a stereocenter because we have 4 different groups. But when you start assigning the configuration, we see that it's a carbon and a carbon. So we have to break the tie. Okay. So let's look at this. So we look at this atom here and see what's directly attached to it. CHH. We do the exact same thing for this one. And we see we have a CHH. So when you analyze this, you see a carbon and a carbon, same, hydrogen and a hydrogen, hydrogen and a hydrogen. There's no tie, or there is no tiebreaker. It's still a tie, so we have to take another step. So at the point, if we get a tie, once again, you just go to the next atom. So now we move to, let's see here, it's not working. So here we have a tie, because we can see these red atoms and these red atoms are exactly the same. So now we go one step further away, or one atom away from the stereocenter. So now we are focusing on this carbon. And we're focusing on this carbon. And we are asking what's directly attached to that, ignoring everything before it. So you can see that we have 2 hydrogens there and a carbon there. And we prioritize it. Right there, carbon HH. And then we see here on this carbon, right here, we have a chlorine and 2 hydrogens. And we list them in priority. And then we just go through the same analysis as we did on the left side over here. Carbon, carbon, hydrogen, 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 hydrogen. Tie. Carbon, chlorine. Oh, those are different. Which one's larger? The chlorine. So that means this carbon right here is going to take priority number 2. And now they are ranked or prioritized properly. And then we just go through and do our arrows. So if that's 1, that's 2, that's 3, and 4, we see that we go 1, 2, 3. So we are going clockwise. So that would make that a R. And that's what that's what this slide is showing us here. Okay. So this is the flow chart of how we did it. Okay, this is our original. We then look at the next carbons, we look at the carbons and what's attached to it. We get a tie, so we have to move to the next carbons, and then we see if we can break the tie. And if you can't, if you can't break the tie on the 3rd try, you just keep going out further and further and further until you find a difference. And if you don't find a difference, then it's actually not a stereocenter. The groups are exactly the same. And so you made a mistake. Okay? So what I mean by that is, let's say we have a molecule that looks like this. Now, this is not a stereocenter because we have 2 groups that are exactly the same. But let's just say you made the mistake and thought it was a stereocenter. You would go to this carbon, and that's a carbon. So how would you break the tie in prioritizing? Well, you would see that this carbon right here is attached to a carbon and a hydrogen and a hydrogen. The same thing with this guy. We have a carbon, hydrogen, hydrogen. So there's a tie. So then your instinct tells you, well, you got to go to the next carbon. And that carbon is attached to a hydrogen, hydrogen, hydrogen. And that also has the same thing. So you have a tie, and now you're at the end of your rope. There's no more carbons to jump to. And now you see that it's a tie all the way through, and that's evidence for you to say, oh, oops, I made a mistake in that this is not a stereocenter. Because the 2 groups right here are the same. Okay, now let's look at this molecule here. We have a stereocenter right there. But how do we prioritize this? Because look at the groups. They're clearly different. We have a methyl, we have an alkene, and we have this propyl group and a hydrogen. 4 different looking groups. So we know it's a stereocenter. But how do we prioritize it? Because we have a carbon, carbon, carbon. So the only thing that we know at this point in the game is that the hydrogen is the lowest priority. We know that for a fact. But the 3 carbons, we need to figure out what to do. Now, when you have alkenes in the molecule, there's a trick that we use to help determine the priorities. And that's shown in these panels here. So, if you have something like this, okay, an alkene. So this right here represents our situation right here. Do you see how this bond right here is attached to the stereocenter? That's what this bond is showing, that this bond right here is attached to the stereocenter. Okay, and what we do is we fictionally draw another molecule in which we take this carbon right there and put it there, and then this carbon we take it and put it there. So another way of saying it is that if I numbered that carbon A and that carbon B, we are taking carbon A and sticking it there, and this carbon right here would be carbon B. You see how we're just doing a switch? So we get rid of the double bond in this structure, and we take those carbons and we turn them into single bonds. Okay? So if you have, in this example right here, when prioritizing, you get rid of the double bond. And you take this atom right here and you switch it. You see how we took the nitrogen and stuck it on that carbon and then stuck a carbon on that nitrogen? Now we're doing this just so we can prioritize. Okay, we're not actually doing this in the lab. We're not changing the molecule. We're just doing this as a trick. Okay, so this would be treated as this guy. And so you can go through all these examples. I will mention this one right here. When there's a triple bond, you then add nitrogen twice. And then you would add carbon to the nitrogen twice, shown there. Okay? So now you take this molecule right here and redraw it using these rules that I've shown you above. So let's take our molecule. This is right here. We have a stereocenter. And now we replace those double bonds with what we've shown. And since there's 2 carbons in between, we just add carbons. And that's what we see. 2 carbons. Okay? Now we start to prioritize, just like we normally have. Here's our stereocenter. So let's look at this carbon right here. What's directly attached to it? What's directly attached to this carbon that I'm pointing to? Well, we see that we have these 2 hydrogens and this carbon. And that's what we see here. Okay? Now we just do that for every single carbon. What about this guy? Well, it's only attached to 3 hydrogens. Okay? And then this guy. We see that it is attached to this red carbon, a hydrogen, and that carbon. So 2 carbons and a hydrogen. And now you just compare these 3 and see which one has the most, which one's the heaviest. Really. So if you compare these 2 together, you can see that there's a point of difference at the first carbon. So this one takes priority. This one takes priority. And then if you compare these 2, you can see same, up. There's a point of difference right there. So this carbon right here takes priority 1, priority 2, and priority 3. And now you can go. So when we're going through our steps 1 is to identify or prioritize the 4 groups. When you have double bonds and triple bonds, it takes a little bit more work. Okay. And when we do that, what are we going to get? Well, the answer is shown at the bottom of the screen, but I like to put my numbers here. 3, 2, and 4. And then I trace it 1, 2, 3. So we are going in the counterclockwise direction, which means that is a S. Okay. Now we also have to be able to describe the configuration of the stereocenters in Fischer projections. Okay? So when we look at the Fischer projection right here, we need to identify the stereocenters. And there they are. There's two stereocenters. Now looking at the top stereocenter, we see that the lowest priority group, which is this one right there, is a dash. Because that's what Newman projections tell us, right? Because if we look at a generic Fischer projection here, okay, let's go X, Y, A, and B. What does that tell us? It's actually telling us it's looking like this. Right? So you can see that the lowest priority here is going to be a dash. And that's what we want. So it's oriented just right. And so all we have to do now is prioritize the groups around that stereocenter. As shown there on the slide, we go boom. So that's going to be a R configuration because we're going clockwise. But now looking at this stereocenter at the bottom, we see that the lowest priority is now a wedge. So that's a problem. But you cannot rotate and flip Fischer projections. You have to just leave them alone. But because the lowest priority here is a wedge, we can do the opposite trick. So we just prioritize, we do our arrow here, and we see that we're going in the clockwise direction. So that should be R, but we take the opposite because the hydrogen is a wedge, and it gives us a S configuration. And so you can see that this is a very simple Fischer projection. When you start looking at sugars and other molecules that are larger, there's just going to be more to it. But just because it's large doesn't mean it's impossible or it needs to be daunting. You just take one stereocenter at a time. So if you have 4 or 5 or 6 stereocenters, just relax, do them one at a time. So I talked about this previously, in which if this wasn't here, and I asked you, what is the relationship between these two molecules? And you didn't have this information here, okay? You didn't have the names. So all you had was the molecules. And I asked you, what is the relationship between these? Well, the first way that I taught you is, rotate the molecules, orient them to see if this molecule B is a mirror reflection of A. And if it's a mirror reflection and it's superimposable, then they're identical. If they're a mirror image and they're non-superimposable, then they are an enantiomer. If B is not a mirror image and not superimposable, then they're diastereomers. Okay? That requires a lot of mental manipulation of these molecules. Okay? And for some people, that is rather difficult. So here is another way that you could do it. You could name them. Name both of them. Okay? So now we have our names. And then you identify the stereocenters and write down what the configurations are. Okay? So this one would be the RSS, and this would be the SRR. Now you can see that on molecule A versus molecule B, that the configurations are completely opposite. And when the configurations are all completely opposite, then you have enantiomers. But when you look and you see some are opposite, like these right here, and then some stay the same, then you know you have a diastereomer. So if you're really good at assigning configurations to the stereocenters and are horrible at manipulating molecules mentally in three-dimensional space, then this might be a good technique for you to use to identify enantiomers, diastereomers, and whatnot. So if we go back to this molecule, what if, okay, now I'm making a modification here. What if this molecule didn't look like this and it was twisted and distorted and just was crazy looking? And I asked you what's the relationship between A and B. What you could do, even if this molecule is distorted and all crazy like, okay, well, let me show you what I mean. So let me go to a program here that I have. And let me double check. Okay, so let's draw that molecule. How many carbons are in there? 1, 2, 3, 4, 5, 6. So I got one too many carbons. Okay, now we have all dashes. Okay, dash, dash, and a dash. We'll add the chlorines. Okay, so we have that molecule here. We'll put it there. And let's copy and paste this. Put it there, but now let's replace those alpha wedges. So we already know the answer, right? What's the relationship? They're enantiomers. Okay? So if we call this one on the left, molecule A, this on molecule on the right, molecule B, we see A and B are enantiomers of one another. But what if I did something like this? Took B and did this. Clearly, you can see that they're identical, right? Because they're superimposable. But what if I took this molecule on the right and I changed the way it looks? What if I did that? So all I'm doing is I'm just orienting it in different three-dimensional space here. Okay. I want to try to get it to look a little bit more crazy, and it's just not doing it for me. Okay. But if I make it look crazy looking, how do I know both of these are identical? Well, you would go and you would see that if you can follow my cursor here, does this have a draw function? I don't think this, maybe it does. Okay, it doesn't have a really good draw function here. But what you can find is that this stereocenter right here is an RSS, and this is an RSS. If you have the same configuration of all the stereocenters, then you know you have the same molecule. Okay. Okay. Let's take a look at this molecule right here. Not that. There's an alkene. What is that? A trans or a cis? We know that's a trans. What about this alkene? We see that is a cis. Okay. And we've gone over how to figure that out before. But what about this alkene? I want to go to my other writing program. It's easier. What about this one? Is that cis or trans? Well, remember, we have to then, how do we figure out if this was cis or trans? We drew a line through the double bond. We see that there's a hydrogen and a hydrogen. Okay? And then we circle the largest group on each half. So that's the larger group and that's the larger group. And then we ask ourselves, what's the relationship between those two large groups? If they're on opposite sides of that alkene, then they're trans, right? So if we attempt to do that for this guy, we can see that this right here is the larger group, and this is the larger group, okay? So those two groups are trans to one another. Makes sense, right? But if we do this analysis again, what is the relationship between the methyl group on the left and the methyl group on the right? The relationship between those two groups is cis. So how do you describe and discuss this molecule with someone? It's going to get very confusing. Are you talking about the bromine and the methyl group are trans? Or are you talking about the two methyl groups? Are they cis? And so it's going to get very, very confusing really, really quickly. So we have to use a different system to describe the configuration of a double bond. And we use what's called a Z and E system. Okay. And here's the rules on how to designate if an alkene is E or Z. Well, let's just show you, okay? So what you do is you look at a alkene, okay? And you split it in half again like I've said, okay? And then on the left side, you identify the highest priority based off of size. And then you do the same thing on the right side. What's the highest priority? And if the highest priorities are on the same side of the alkene, we call that a Z configuration. Z standing for same side. Do you see the pun there? Same side, same side. I know it's stupid, but it works. And when you look at the figure on the right here, you see the highest priorities are on opposite sides of the double bond. So we call that an E configuration. E standing for opposite side. So we have the same side and the opposite sides. Okay. Really, really silly, but by golly, it works, and it has never left me for these 15 years of being in school. Okay. So that's how you keep track of it. So if you look at this example right, so let's just go back to this molecule right here. So what type of isomer is this? Is it a E or a Z? Well, we do our process. Divide the molecule in half, identify the highest priority. Okay? Those are on the opposite side. So that makes this a E. If you wanted to look at the diastereomer of this molecule, but the Z diastereomer, what would it look like? It would look like that. Because these groups right here are on the same side. Now, okay, let's see here. Now, on this slide, what I want to show you is that when you name an alkene, we see the correct name. But now, you see how pentuene, the same name, but they're clearly diastereomers of one another. They're different molecules. They're going to have different physical properties, but they have the same parent name. So how do we distinguish between these two? Well, we have to use the Z and the E. And so you just stick the Z in parentheses at the beginning of the name. So we have the Z pentene and then the E pentuene. Okay? You just have to, so we're just adding another layer of understanding to how to name molecules. Z and E. Okay? But what happens when you have multiple multiple double bonds? How do you name molecules like that? The isomer on the left, we see that there's two double bonds. But this double bond right here at carbon 1 and 2 does not get an E or Z assignment because it has the two hydrogens on carbon 1. So there's no such thing as a E or Z for this guy. But the alkene at carbon 3 and 4 does have can be assigned an E and a Z. And we see that it is going to be an E because when you take and do our trick, draw a bond there, and find, so we have a hydrogen there and a hydrogen there. There's our methyl, and then there's this piece. And you can see that they are on opposite sides of one another. Hence we assign the E. And in the name, we just put an E at the very beginning because there's only one alkene in the name that can be a E or Z configuration. So this E right here does not apply to that guy. We already know that because we see, well, if we just look at just the name, we see that there's a diene. So that means that there's two alkenes. And this E clearly is talking about the third alkene because the first one cannot be an E or a Z. It's just implied. But when you look at the molecule on the right, you can see that this double bond can be an E or a Z, and this double bond could be an E or a Z. You have to figure out what it is. And we see that at this carbon, this double bond right here is a E. So we, in the name, at the beginning of the name, we specify where the alkene is with the number. It starts at carbon 1, and that alkene is a E. And then the second alkene starts at carbon 3, and we see that that is a Z. Okay. Now, why is the alkene at carbon 3 a Z? Well, if you draw your plane there, you can see the methyl group and this group, or this whole thing actually, is on the same side. Okay. So it takes practice looking at molecules when they're larger and just bringing it back to the baby steps, or the very simple way we started looking at things. See, this is the very simple, the most basic way of looking at the E and the Z configurations. And you just apply that to molecules that look a little bit nastier. Okay? Always go back to the basics. Okay? When you're solving organic chemistry problems. And that is the end of chapter or interchapter C. So if you have any questions, as always, please reach out. I'm more than willing to work with you in groups or one-on-one. I'm here for you. I'm here to help. Okay?